Hey there, everybody. And yeah, hope you're all doing really great today. Actually, going to see if I can maybe use another microphone today. Can you all hear me? Put my microphone closer to my voice. Please let me know if you can hear me in the comments. Happy Holi to those who celebrate it. Happy Global Hack Week. We are on, I think, day 4 of Global Hack Week. Is that right? Someone maybe correct me on that. Is it day 4? I think so. Really, really great to see you. And yeah, we're going to be talking a little bit about machine learning today and how we could use machine learning potentially for some really useful application, and in this case, for agricultural application, for detecting ripe fruit. Have you ever wanted to know? Should I eat that fruit? I'll tell you all a story from yesterday. Actually, I was at the grocery store and I was looking for a mango because mangoes were on sale at my grocery store. And I bought a mango. It felt really squishy, not too squishy, but just a little squishy, and it smelled good. I said, this will be the mango. And I brought it home and I cut it open, and it was way too ripe, way too ripe. And I was just thinking, man, this is like, I don't know, some kind of like funny trick, because I'm gonna go talk about overripe fruit tomorrow. And here I am eating an overripe mango. But yeah, we're gonna be talking about that today. And before we get started, I want to make sure that everybody has a chance to check in. So here's our slides for today, and just would love for you to check into the stream. And it only takes a second to do, but when you do that, it lets us know that you're interested in this kind of content. And yeah, that's super, super helpful for us. It also gets you some points for your guild. So I highly recommend you to sign in for that reason as well. How's everybody feeling today, by the way? Where are you logging on from? What time zone? Are you tired? Is it the end of the day? Are you excited to start your day? I'm personally excited to start my day. It's the morning here in California, and yeah, gonna grab some coffee during one of our breaks. Someone in the chat says 6:30 p.m. That's a good time. I feel like 6:30 is a good time to unwind after some work. And Trina says, happily, this is my lunch hour. That's awesome. London, wow. I would love to visit there. Excellent. So maybe some of you had lunch. I hope that your lunch does not include any overripe fruits. That would be a real bummer. But, we're going to first give some background on classification algorithms, because first we checked in. Second, we'll give some background on classification algorithms. These are really what we're going to be using to determine whether our fruits are too ripe. Just a few common algorithms for you to think about for classification. The first few, logistic regression. This is very similar to what we're going to be doing today, although not the same, but it's involving a linear model. We also have some other ones that could be maybe considered like a clustering algorithm. For example, number 6, K means clustering. But all of these algorithms, if you hear these words, it means that yeah, you're dealing with a classification problem, deciding what is this data, and putting it in some category. So let's just look at some diagrams for classification algorithms. A classification algorithm takes raw data and predicts its category. So, for example, we could have a fruit classification algorithm where we have a color of the fruit, the size of the fruit, and the weight of the fruit. So let's assume that the fruit is blue, it's very small, and it's very light. Um, we as humans, we can easily tell that is a blueberry. It's not a pear. But the if we train a computer, it may be able to tell that as well. Here's another example of a classification algorithm taking in raw information and predicting its category. This is email spam. So, actually, not email spam. This is making a decision about the groceries. Sorry, I forgot to change that wording. But basically, imagine you know what time of day it is, and you know the traffic levels and how much food you have in the fridge and how hungry you are. You can make a decision about whether to go to the grocery store and get some food, or to stay home and just relax, maybe. And a classification algorithm could also help you make that decision. And finally, this is the email spam example. So you could consider the sender of the email, the send time, the subject, and the body, meaning the content of the message, and classify that as either spam or as an email that we really should read. But how do we construct an algorithm specific to our needs? Well, we want to consider the type of learning involved. So, this is probably the biggest um, factor in determining what will be the proper algorithm, proper approach for our research question. And there's major types. So, for example, there's supervised learning, where models learn from training examples provided by humans. And this basically means that someone has to go out there and give the model some examples to work off of. And then the model can be calibrated to see an unknown example. And supervised algorithms are mostly used for discrimination. So that means recognition tasks. A lot of people think the word discrimination always means bad word, is actually just a way to determine between two things, um, at least in this context. So we will split the data into trained data and test data. The first category being usually a lot larger than the second, but the training set is the calibration, and the test set tells us how well the calibration worked. So we typically see 80%, 20% split between these categories, where training is like 80% of the data allocated and test is like 20% of the data allocated. So this is an example. So we could potentially think about random forest as an example of a supervised algorithm. And lecture 3, that refers to lecture 3 from last month, where we did a little bit of random forest investigation. So I recommend you check that out. But yeah, all 3 of these are apples. But if the machine has never seen an apple on its side or an apple cut in half, then it will never know that that is an apple. So we need to give examples for supervised learning. There's also another kind of learning called unsupervised learning. And unsupervised learning is kind of different. Before I go on to that, does anyone have any questions about supervised learning? If so, please put them in the chat. I'm happy to stop at any time. I watch the chat as we go, and happy to stop and yeah, give you any answers to any questions you might have. But unsupervised learning is when a model learns from unlabeled data. So this time we're not actually giving the model any human generated examples to learn from. We're actually just going to give it generative tasks. So this is kind of like an imagination task. There's no split between the train and test data. And this is from, again, our last month's um, stream. We were looking at the k-means clustering algorithm, which generates these clusters of data. And if you're interested in learning about k-means clustering, I recommend you check out last month's stream. So yeah, totally recommend that one. And as an example, we have the generative adversarial network, which has some classification, has some interesting components to it. But basically, it can take in some parameters like age, eyes, perspective, mood, and through a very complicated algorithm, it can produce an image of someone. So this image, you might think, "Oh my goodness, Stephen, you're putting someone's image out there who didn't give you permission." But actually, this is not a person. This is a computer generated profile. Definitely fooled me when I saw this one. But yeah, so basically, this is the example from unsupervised learning. We also have reinforcement learning. So this is where the model learns the best strategy using a scenario given by humans. We actually covered this scenario in Monday's lecture, where we learned about forest management. And the strategy was whether to cut down the forest or wait, and see it grow. And we were trying to get the most benefit from the forest. So that was really good. And it involves a scenario where we have actions and environment, and is mostly used for decision making tasks. So you could think about robotics as a good example of that. Like robots need to they need to make a decision based on an uncertain environment. So that could be really useful. And that's example is Markov decision process. And we covered Markov decision process again on Monday of this week. So I highly recommend you look at that one if you're interested in learning more about reinforcement learning. But yeah, there's another great YouTube video by Computer File on this topic. And now I'd like to show you a diagram of that learning algorithms. So we want to select your learning mode based on application. So I would like you to look at this diagram and give us a guess in the chat. Where would you put our task for today, figuring out the ripeness of the fruit? Would you put that in unsupervised land or in supervised land? I'll give you a minute to think about that. While you all are thinking about that, I'm going to go heat up some water for my coffee. I'll be right back. Okay. So a few comments there. Hi there. Being Faraz Khan, how are you? Good to see you. And we have a few answers in the chat. Folks saying supervised learning. It is a discrimination task. We are trying to recognize ripeness or unripe. Um, and then another comment. So thank you for that, Trina. And then Indigo Wizard says supervised. It needs to see the object in its different states. Right. So we need to. I love both of those answers because they kind of capture two different aspects of why it's supervised learning. The first being that we need to use a recognition task, and the second being that this algorithm is going to need to see some examples before it can correctly determine whether something is ripe or not. And this is kind of an interesting comment by Shelstronic here. So yeah, so we already know the labels, so supervised. So the labels, I think maybe you mean the different features. Oh no, you mean the different like ripe, unripe. Those are the two labels. Yeah, exactly. That's a really good point. In unsupervised learning, we don't necessarily know that. So that's a really good one as well. And in fact, recognize a ripe fruit versus unripe fruit would be firmly within the supervised category. So we're definitely going to be implementing one of those algorithms. Here's some other factors that we always need to consider when we're building a machine learning model. For one, we need to know how many variables we have. So number of features is kind of a really hard problem for computer vision, actually, because in an image, we don't have such a simple thing as what we had in the examples I showed earlier. Like, for example, in the fruit classification algorithm, we could easily reduce our fruit to size, color, and weight. And those are three features. So easy enough. But when we have pictures and images, it's kind of hard to reduce it into some features. And so we need to think carefully about how we do that, as we will today. But yeah, here's just two examples of some algorithms that do well with either more or less features. And we're always trying to reduce the number of features to simplify our model. That's what is known as feature selection. Another thing to consider is linearity. So is your data linear? And so, there's a lot of stuff to think about here, but basically, this means that if you know there is a linear relationship, in other words, like a directly proportional relationship between two things in your data, that's really great because that means you can be confident in using linear algorithms. Like, for example, this support vector machine algorithm, which draws a straight line in between two parts of your data. And finally, we want to think about training time as well. And this is really related to how much data do you have and how fast is your computer. So if we want faster training, we need to consider an algorithm that is a higher speed, more efficient algorithm. But if we want accuracy, we generally need more training, but that's not always true. So you might want to consider random forest, which doesn't train as fast as a linear algorithm, but it does generally have more accuracy. But of course, we can only use an algorithm that is as good as our computer. So we're going to account for that today, actually, in our workshop. And the number of parameters is important too. So, these two models here have just, for example, 4 parameters and 8 parameters respectively, but we can see millions of parameters. These are basically the little knobs the virtual knobs and buttons on your machine learning algorithm that you can turn and twist and push to sort of optimize your model for the exact task that you're trying to do. And sometimes folks will split their data into three instead of two. You might remember earlier I mentioned that folks will split from train to test data. Well, actually, you can also split from train to validation to test data, and then you can examine the parameter space in this validation step. In other words, you can tweak those model settings. This process can take a really long time, so it's not always something that we engage in, but definitely worthwhile in some contexts to improve your accuracy. Okay, everyone, so we're going to take a quick 10-minute break, and then we're going to go on to our example, which is the computer vision gradient descent example. And yeah, this is going to be really good for us. So before we do that, though, I want to show you the gradient descent algorithm. This is what we're going to be using today. Hang on, let me show you this tab. It's a really cool video, actually. Basically, this algorithm looks at the gradient on some kind of feature map here, where in this case we have two dimensions, right? X and Y. And it can optimize and find the best fit. So these bright yellow spots are like maybe mountains. And let's say this algorithm is trying to minimize, and these blue values are like valleys or canyons. And so all of our points, no matter where they start, they're all trying to go towards a canyon. And you can see that no matter where they start, they all go towards these optimized quantities. And it's actually a very fast algorithm because it is, in a sense, a linear algorithm. You just compute the gradient, and then you figure out which direction to move your little dots or your data points. And then you repeat over and over again until you arrive at the minimum. So that's gradient descent. Pretty fast algorithm, but only useful in certain cases. And just a reminder to all of you that this animation that I showed is a two-dimensional animation, but our image actually has a lot more dimensions than just two. We have color, for example, in our image, which is going to be really complex. You can also think about our image as having other dimensions, like the shape of the banana, the foreground, the background. That's kind of a little more abstract, but yeah, there's a lot of dimensions of information embedded in our image. And we're going to use this gradient descent algorithm in a larger process called transfer learning. And so what is transfer learning, you might ask? Has anybody used transfer learning or the gradient descent algorithm? If so, give us a chat, a mention in the chat. Let us know if you're familiar with these methods. But basically, transfer learning involves using a previously trained neural net to extract certain features. And so this data set could be trained on over 1 million images using CNN algorithm or some other really involved algorithm that has multiple hyperparameters, and it's been tuned exactly right by whoever made this this pre-trained image model is what they're called. And then on top of that image model, that image model is basically going to do feature selection for us. It will figure out what the important features of the image are, not unlike what we were doing earlier, where we were saying, okay, what's the size of the fruit? What's the color of the fruit? It'll do similar things like that. Then we can add a final classification layer right on top of this image model. And in our case, we're going to use a model called gradient descent, which we explained in the previous slide. This final layer is actually faster and requires less training data. So for that reason, and we should all be able to use it, which is great. And then we'll get a result. Okay. So we're also going to use something called a confusion matrix to assess our results. So if anyone in the chat has used confusion matrix, let us know. I see Rahun Khan has experience using transfer learning, so that's awesome. I hope that maybe maybe this will be useful as well for you. But let's look at this table. This table is telling us on the y-axis, or in the rows, the actual condition of the data. So the population has positive and negative results in this case. In our case, we could maybe call this as ripe or unripe. And then it has its predicted conditions. So that's positive prediction and predicted negative. So for example, if the model predicts that an image is a ripe fruit, but the actual condition is that it's unripe, that would be what we call a false positive. And this matrix will tell us where our model is messing up, in a sense. Okay. So we'll do an example after the break. Let's actually go back to here. But for now, I want to actually ask you all to download something from a Google Drive link. I kind of sound like maybe, sometimes you get an email that says, oh, download these pictures from Google Drive. Don't do that. That's a scam. But this is not a scam, I promise you. This is a Google Drive link. It's asking you to download an image data set. This data set being a bunch of bananas that are either ripe, unripe, a little bit ripe, maybe too overripe. And we're going to use those images to train our transfer learning model. But we'll do that after the break, and I'll see you all in just about 10 minutes. Hey everyone, we are back and welcome back to the stream. I hope that you had a good little break there. It's always good to take breaks while you are working, and Global Hack Week is no different from that. Make sure you're taking care of yourselves out there. And yeah, during the break, I made my coffee, and I actually was thinking about. So yesterday, I had a really hot drink, and I burned a little bit of my tongue because I drank it too early. Does that ever happen to any of you? But the message there is always wait for your drink to be definitely not too hot, because now when I drink my coffee, because I burn my tongue, um, you know, I can feel it. So, just wait another 5 minutes before your drink is nice and warm, not too hot, because you'll thank yourself days later when you don't have a little burn on your tongue. Okay. So that there's a public service announcement for all of you. Um, don't, just wait for your drink to be not too hot. Don't forget about that. Okay, so I hope that you all were able to download those images. Um, Let me know if you were unable to use that link. I think that link should work just fine to download the images, but let me know. Um, yeah, let's move back through what we reviewed before the break. Just a quick review here. So we're going to be using the gradient descent algorithm, and it involves this process of sort of moving these data points into converging them into these minimum solutions, or these optimal solutions, you could say. And it's really fast. So we're going to put it on top of a pre-trained image model that is pre-trained with over 1 million images using a CNN algorithm to figure out what is the best features to extract from the image. And then we hope to get an accurate result. And we also talked about the confusion matrix. So this is a way of figuring out whether our classification algorithm is accurate or not. And we're going to be implementing the confusion matrix today. So those are just a few, reviews, but I'll paste in the chat the link to this notebook. It's actually a notebook created by the TensorFlow community. TensorFlow being a popular machine learning library that is used in Python. So if you are familiar with TensorFlow, that's great. If you're not, that's okay. This tutorial will help us to learn. Um, so let's go ahead and do that one. Okay. Let me show here. So I highly recommend clicking this button, run in Google Colab. That'll get you running without needing to install anything at all. It'll just work. So we'll click on Run in Google Colab. Let me switch to this one, and we can run through the cells. So if you're in Google Colab, there are these cells of Python code, and you can run them by clicking on this play button here. And then it loads for a little while. The first time you try to run a cell, it has to connect and initialize, kind of give you a little bit of virtual computing space to do your work. But once you do that first command, everything will run much faster. As we were talking about earlier, we're going to be using transfer learning today. And so, we know that convolutional neural networks are really great for classifying images, but the problem is that they're really hard to run. So we will use a pre-trained image model to do that. And we need to import some libraries to get started. We're importing a lot of stuff in Python, native Python, but we're also importing TensorFlow stuff. And this is going to be our image model right here that we import. So let's run that cell so that we can import all of the libraries that we'll need. And for this example, before we start with our ripe or unripe fruit example, we're going to be looking at the flowers data set, which is just this flower data set that it comes with TensorFlow. It's a really good way to kind of get started without using any data. If you don't have any data, you can just use this example data. But yeah, so our flower directory was where we'll put all the photos, and each of those will be separated into a subdirectory where we'll put all the examples. Um, our train fraction will be 0.8. This is what we were speaking about earlier, where we need to make sure there's an 80%, 20% split between our training and our testing data. The testing data is what we'll use to generate that confusion matrix we described earlier. And then our random seed is just to get the model started somewhere. It's kind of just important to do. But these functions that were created by the TensorFlow library, we don't need those for our example, but they're great for downloading the flower data. And then this function, make, train, and test sets, will actually split the data into those two categories. And in particular, you can see in this line here, it is walking through that flowers directory that we defined. And it's kind of separating all of the data according to these subdirectories, assigning them to their classes, things like that. So it's really, really important function, this train test split function. Let's run this code cell. And say it's really quick to run because we're just defining the functions. That's all that's happening in this file, in this cell. All right, now we're going to download the images and split them into train and test sets. So you can see we are going to have a variable called train examples, test examples, and then classes. So here's the classes over here. You can see them: daisy, dandelion, roses, sunflowers, and tulips. So we have 5 different flower types. And our goal is to use this supervised learning approach to figure out, oh, is this a dandelion? Is this a daisy? What is this? And this data set has 2,934 training images and 736 test images. Make sure you note that the TensorFlow package has basically randomly allocated these images. And that's really important because you want your test set to be an unbiased representation of the population. And you want your training set to also be an unbiased representation of the population. So to do that, you need to use a random sample. Now we'll explore the data a little bit. So yeah, this part of the notebook is it's actually not related to machine learning, but it's just giving us a few examples of the data so that we can better see it. So here it is. You can see there's a picture of a dandelion, for example. There's a picture of a rose. And, this is what we were talking about earlier with supervised learning. It's giving the computer some human-generated information. Humans took all these pictures and labeled all these pictures. And now it's going to be the job of the machine to learn from those examples to build its new model. Okay. Any questions so far? If anyone has a question, please feel free to send a message in the chat. I'm more than happy to answer those questions. But if not, we'll continue along with our build the model step. So we will load a TF hub, which is a TensorFlow hub image feature vector model. And then we'll put a linear classifier on it and add training and evaluation operations. So, this cell right here is going to build the TensorFlow graph that describes the model and its training. We have a learning rate, which says how much the model should change each iteration. And then we'll reset to the default and import this image module. So right here, this image module is that pre-trained model that we were talking about. This is what takes a really long time to train. And you can see that it's already been created. All we need to do, and it's available at this address, all we need to do is import it. There's a lot of different choices as well as the comment says. So I highly recommend playing around with that image model and seeing if you can come up with something that works even better than what we have today. But then we will pre-process the images into tensors with size expected by the image module. So tensors are just sort of multi-dimensional arrays, and it'll sort of get all of the important features from our image. Decode and resize. This is going to, decode any JPEG images, resize the images so that they all have a similar size. And so, not to get too hung up in this code, but basically we have, we're creating our model in this function here, create model. This is an important one, actually. We have our single layer, but we could actually create multiple layers if we wanted to. For example, adding additional layers, it can improve the accuracy of our model, but not always necessary, and it does add to the time that it's used. Okay, so you can see here that for each class, the model outputs a real number as a score of how much input resembles the class. So we could then just say, like, maybe pick the highest number of all of the numbers from each class, and then that is the one that we will choose for the result. So that's totally fine. And I want to just focus now on this portion here where we are adding in our gradient descent optimizer. So this is that final layer that I was discussing earlier, which is going to be really fast, linear model, and it's going to work on top of this dense CNN network pre-trained image model. So it's going to be minimizing the loss function. In other words, trying to find that best fit. And we have a few variables here. So our probabilities is going to give us those probabilities of each class. How likely it might be that this new image comes from, for example, the rose class or the dandelion class. And then we're choosing the one that has the highest value, just as you might expect. And then we see if that is equal to the prediction. So the prediction and then the highest probability will be put there, and we can figure out what the accuracy is from there. So let's run this cell. Okay. And so now that we've done that, we're going to train our network. So this is the portion where we're going to utilize that training data set and actually use that. Someone says they have a project regarding classroom lights. That's an interesting question. Maybe we can save that question for the end and brainstorm together. If anyone has any ideas for Devasai, I highly recommend you respond in the chat to give that, but we can totally talk about that later. Anyway, so we can give a number of training steps, and actually the number of training steps, the more you give, generally speaking, the better the model will perform up to a point. And then the training batch size tells us how many examples to use in each iteration. That will also be very important to the accuracy. And then it will evaluate the model every so often. So in this case, we're evaluating the model every 10 as well. Okay, so these functions will get our examples from the training data, get the images and labels, and it will basically run a batch to train the model and figure out what is the accuracy of that model as it's currently configured. How will it perform at each step? So let's run this cell. Okay, so you can see at these first early steps, step 0, we have a pretty poor accuracy of the model, just 34% of the time getting the answer correct. But as we go higher and higher through the steps, our accuracy increases. And you can see that it sort of converges. As we go to higher and higher training steps, the model's getting better, but not that much better. And then once we get to our last stage, which is step 100, we get our best possible results. So that's 80% accurate at predicting what kind of flower is this. Okay, that's pretty cool, honestly. It's not as good as a human, I'm sure, but we've made a pretty impressive model with pretty limited resources. And now we're going to show the confusion matrix, which will tell us exactly where our algorithm is messing up. So here's how to read this confusion matrix. On the bottom row, you have our predicted labels. So let's say that the model predicted that a certain image was a daisy. Okay. Then what was the real result? Well, 0.8, the fraction, it was daisy. But some of the time, it was actually a dandelion or a tulip. So that's what these numbers are here are showing, is that the majority of the time it was in fact really a daisy. And you can see which of these classes that the model had the hardest time with. So in this roses case, the model had a really hard time. So I think roses were the hardest for the model to actually do. And you can see the math here. So they are taking the confusion and then dividing by the sum across that whole axis. So that's kind of how each of these numbers is generated. Okay, so that is the basic idea here, and we're gonna also use this for our ripe fruit example. The TensorFlow notebook has also put in this nice little example so we can look at the incorrect images. And that's a really good task to do because, maybe you are like, wait a minute, why is it messing up? One of them could be because it has this big background, this landscape, or maybe because the flowers are in a vase here. So you never know. But there's plenty of ways to improve the model. So you can definitely try these at home. Trying a different image model and adding more layers. So this could be adding more layers between the image features and the linear classifier. We could change the hyperparameters. So this could, for example, increase the number of training steps from 100 to 200. Will that be better if you change the learning rate of the model? Could that affect it? So that's definitely worth looking into. And finally, trying a different optimizer. So replacing that basic gradient descent optimizer with something more sophisticated. Would that actually help your algorithm to predict these flowers? Those are all things you can try at home. But I'm going to challenge you all, actually. I'm going to give you a little bit of time to play with this notebook. And I'd like you to here's what I'd like you to do. I'd like you to implement this code for the ripe, unripe bananas. So what you can do is you can go to File and you can click Save a Copy in Drive. By doing that, you're going to get your own copy of the code that you can play with in your own Google Drive. So let's see. Let me share that with you. Share this tab instead. And then in this folder section here, it says we need to connect to a runtime to enable file browsing. Don't worry about that. It should be connecting right now. But basically, I want you to upload those image files into your drive and see if you can get them working. All right. So that's the idea here. I'm going to give about 5 minutes for you to go through that. And yeah, try it on your own, and then we'll return back. Okay, everyone, we are back. And so I'd be really curious to know if you all were able to implement this. Please leave a chat message if you were able to try this on your own, and if you were able to get any results. Yeah, it would be really interesting to know. And let me know what the score of your model was. How good was your model at evaluating the ripeness of the fruit? But I just want to first take a second to acknowledge this work that we are using today. So we are basing our research off of this paper, Banana Ripeness Stage Identification, a deep learning approach. So this paper used a convolutional neural network to get a feature accuracy of 96.14%. So they're using this CNN model. Um, and they use some other techniques that we did not use today. But yeah, they're also implementing transfer learning in their work. But we're just going to see if we can get a good result from our simple approach. Maybe we can get a result that's almost as good as this paper. So if you download their data is at the bottom here. You just click on data availability, click it. I put a link to it in the chat as well. But if you click on that, you can get your data. You can download it to your Google Drive. And I put that in my Drive folder. So I have my Drive and then banana data. And so, for example, let's look at the yellowish green. We can see all of these images. Just a banana that somebody had to go ahead and take a picture of, and say, yeah, that's the yellowish green banana. But then hopefully in the future, the machine learning algorithm will be able to do that for us. And we do not need to have a human do that task. Okay, so let me show you what I was able to come up with for applying this TensorFlow tutorial to our fruit ripeness example. So first, you need to mount your Google Drive into Google Colab. So to do that, you use this code from google.colab import drive.mount content drive. So I'm going to copy this and actually paste it into the chat so that you all can see. Hi there. I love that little icon there. What a cool banana. So thank you for sharing that. That fox with the banana. That's so cute. Okay, so here's the code. And once you have that mounted, we can actually access this directory by clicking on the file button. I'm not going to click there because, well, there's not anything really sensitive there, but it's linked to my drive, my Google Drive. So it has all my folders in there, just not really relevant to the workshop. But then you need to replace the flowers directory with your drive directory. So you put drive/my drive/banana data. And that's going to put you into that folder that you uploaded to your Google Drive of all this banana training data. And actually, I kept everything else the same. So then when you run this, of course, you don't need to run the download data section. Actually, I should say that as well. So in this cell here, we used to have another line that was download data. Oh, sorry. There used to be another line here. We'll just delete download data, which would be over here. I think that's an unnecessary step now. But everything else is the same. And we can look at some of the labeled images just like we did in the Google Drive. So here's all of these categories. We have mid-ripen, green, over-ripen, yellowish green. So basically mid-ripen is more or less, and yellowish green, depending on your preference, of course. Some people like their bananas to be a little bit more ripe than others, but those are kind of the ideal cases. But once we build our model, let's see, and train that. Let's see what the results were. So we got 19. We start off with 19% accurate. That's pretty low. But then this model quickly jumped up to 94.64%, which is just shy of the 96% that the research paper achieved. So with our little transfer learning approach, we were able to get pretty good results. And this is without manipulating any of the parameters, the hyperparameters. So maybe we could do better with that. But if we look at the confusion matrix, then you can see on the bottom, if you remember, these are the predicted values. So you can see actually the model classified overripen 100% of the time correctly, and green 100% of the time correctly. The times that it got it wrong were when we were looking at this mid-ripen and this yellowish green, these kind of in-between cases where it's not so clear whether the banana is yellowish green or mid-ripen. And actually, yeah, you can see in these little cells here, like this one, yellowish green is basically mistaken for mid-ripen some small portion of the time, and mid-ripen is mistaken for yellowish green also occasionally. So that's sort of the result of our fruit ripening. And yes, someone asked, can you please share this collab notebook after the session? Absolutely. I am totally happy to do that. Let me share that with you. I think I can just share like this. So now you can all view and download and copy this notebook at your leisure. I'll paste it in the chat for you. So if you are interested and in checking out this notebook, feel free to. But yeah, basically we've achieved a pretty good result with kind of a limited training period. Let's see here. Applications to fruit ripeness. Where is that? There it is. I'm also going to add in on the top. I'm going to add in this one from our last. It's actually a text. Our last notebook. Just add that in there so that you all can check it out. The previous one. So, okay. Well, I hope you all are enjoy the workshop, and I hope you all are enjoying Global Hack Week. If anyone has any questions, please let me know. I'm also around in the Discord. If you send me a message, I would be totally happy to respond to that. Try out this new thing, this new transfer learning thing on any image data set that you might have. It would be really cool to see the possible results that you come up with. And, now you can do things that are really comparable in accuracy to what the state-of-the-art research is doing with big supercomputers, but you can do it with transfer learning. Yeah, congratulations on making it all the way through the workshop. All right, take care, everybody.